Good morning and welcome to the first session in MCC2 for Thursday. I'd like to introduce Hugh Fisher, a computer graphics programmer and system administration who often works in Linux. Originally a real-time virtual reality developer, the post-Avatar interest in 3D has led him to providing programming and technical support for a local 3D film company. Over to you, Hugh.
Okay, good morning everybody. So this talk's going to ramble a bit. If I start talking too fast, I'm told I do this from time to time, wave at me to yell slow down. If you have a really quick question, sing out and I will repeat the question, so it goes on the audio track. If you've got a really complicated question, you have to talk to Owen here about getting the radio mic. So, stereographic filmmaking in Linux. First of all, stereoscopic films. You may have noticed the past couple of years these have become really big. Started with Avatar. It's now moved into TV sets. It's very difficult. Looks okay on here. Crap. Display 1024 by 768.
Maybe it's pull it over.
So, okay, we'll have to run it like that, I guess. Sorry, where was I? Yeah. You may have noticed 3D movies are very popular. You can't buy a TV set these days. It's not advertised as 3D capable. And it's something with terminal... Yep.
One more thing, your microphone could be perhaps a bit closer to your mouth.
Is that better? Joys of giving talks. Okay, so this was a terminology problem. GIMP and Inkscape are traditionally thought of as 2D programs, and Blender as 3D. And if you're a programmer, Cairo or Excel, it is 2D, and OpenGL is 3D, but now we have this extra usage of 3D as stereoscopic film. So in this talk, when I say something's 3D, I'm always talking about the stereoscopic idea, that you present left and right, different images to left and right eye, creating the illusion of depth. Now in CGI, this is really easy. You just have to render the frames twice. You may have seen Pixar re-releasing all their movies in 3D. And there's a free software solution for that. It's called Blender. They've got a pretty good stereo workflow worked out. So you can do CGI movies in 3D using Blender and other free tools. Now this is a picture I grabbed off the internet of a live action 3D camera. This is what's called a RED digital camera. They made a big splash by introducing digital cameras for filmmaking that only cost about $100,000. They've come down a bit, they're now about $50,000. Now for stereo, you need two of these. And you have a really big bulky rig. And for a recent example, David Attenborough has just put out his first 3D nature documentary. And it's about pterodactyls, long extinct flying reptiles. And in the making of, he's asked, why did you do one about pterodactyls? And he said, well, a 3D camera, it weighs 50 kilograms, you need 4 people to operate it, it takes half an hour to change a lens. The only animal you can get near with one of these things is going to be dead. And that's David Attenborough. He does not get shortchanged on equipment, and that's the best anybody could do for him. So, existing 3D cameras are expensive, they're bulky, they're inflexible, and they're expensive. You can work around the others. The fact that you need 4 people to carry a camera instead of 1, it's a pain, but you can get around it. But expensive is a really big deal. So this is where I come in. My friends Winnie Yang and Nathan Clark, PhD students here at ANU, and a former PhD student who works at Silversun Pictures. They wanted to make a 3D short film. on a PhD budget, which is effectively zero. So for this project, they're my domain experts. If you're at the design talk yesterday, mention was made of personas, about how they made up people. So I was very lucky for this project that I had real people, you know, not some ideal abstracted 3D filmmaker. I'd sort of say, well, this is what I'm going to do, and they'd say, no, 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 we need this. So you can get real people, it's really good. So the first thing is this L-foil camera. It's a full HD camera. It's 1920 by 1080 resolution. It's designed for streaming over Ethernet. Or you can record onto hard disks or SD cards. They're very flexible. It's built around an embedded Linux board. Inside here is a little CPU with 40 mega memory. And since I think it's really cool to show that off, just make sure my network is working. Yeah, so it's pingable. So this is the Internet of Things, the word camera connects such to it. Yeah, it's running Linux, so there's my CPU info. 40 megabytes of memory in a camera, which you need for HD video. Of course, the downside of the Internet of Things is I really should change the root password. You configure this little camera by clicking a web browser at it. Again, it's a camera, and it's got Apache or something inside it. And you can see what's currently coming out of the camera. I'll just close it off, talk. Another nice thing about the L-foil camera is also being small, it can run off a battery. Or at least a battery of reasonable size. I mean, technically you can run anything off a big enough battery. So my friends Winnie and Nathan started building a stereo camera thing. It's called The Rig. It should really come up with a classy code name or something, but at the moment it's The Rig. Looks rather like the robot out of Short Circuit. But you can see here two L-foil cameras. The fact that they're nice and small means you can put them side by side at what's called for 3D filming the interocular distance. It's supposed to match distance between human eyes. There's a bunch of network cables. There's a battery pack, and there's a little laptop. So that's going to run all the configuration. It's going to take care of the recording. There's a viewfinder and some shoulder straps, which you can't see there. So it weighs about 7 kilos. It can be operated by one person, although quite often it's useful to have a second person fiddling with the laptop. It's controlled by a great piece of software called L-foil Vision. A guy called Sebastian Pickelhofer wrote this. I hope I pronounced his name right. It's a Java graphical user interface program for controlling an L-foil camera. It's got a nicer interface than the web pages, because after all the web pages are a user interface designed by embedded system engineers, and they're really not too good at it. So it's a very nice little Java program. It's fully free software, and it's got controls that work together. You can do everything through the web interface, but it gets clunky. You have to remember, if I set this, and I also need to set that and do this and the other. This knows about useful combinations for filmmakers. Originally it was written for a single L-foil camera. Winnie and Nathan hassled him, and he wrote some nice stereo config options. For instance, if you've got two cameras, you obviously want them to start recording at exactly the same time. Or if they don't start at the same time, tell you what the delay between them is. And it's not a real-time recording software, it's a configuration software. You run L-foil Vision, set up your camera saying, I want this frame rate, I want the file stored on this hard disk, I want you to use this resolution, and then you go. Now, so far, I haven't had anything to do with this. I can't take any credit for any of this. Where I came in is to do stereo filming with two cameras. There's a bunch of configuration you need to do that you don't do with a regular camera, as well as focus and brightness and depth of field and all the stuff regular photographers worry about. You have the interocular eye separation distance, because you play games with how far apart the cameras are to enhance or reduce the stereo effect. And there's a toe-in parameter which has the same effect. Good filmmakers, like James Cameron when they do Avatar, create the illusion that you're looking through the screen into another world. And that's by very careful adjustment of all the 3D parameters. Not so good filmmakers do it in post-production and you end up with Clash of the Titans. So to do this, you need a real-time stereoscopic preview. You want to be able to see the stereo image that's both left and right eye images as you're adjusting the camera. So you can say a bit wider, a bit narrower, move it, toe in, whatever. And this is where I come in. In a previous era, the Australian National University here had a virtual reality theatre. And I was lucky enough to be a programmer on this project, which means I know how to do stereoscopic 3D in OpenGL. And I'd worked with the School of Art here on a couple of artistic projects, not stereoscopic ones necessarily. So Winnie and Nathan sort of, oh, we need somebody who can write a 3D program for us, we'll get Hugh. And this is where I come in. So, statement of problem, we have 2 video streams. Each of them is high definition video, 1920 by 1080. It's what's called raw Bayer format, and I'll explain that in a little while. You've got to decode this to RGB format and display in stereo. And for stereo display, we use good old red-blue glasses. If you're going to do 3D, this is actually a really good option because it works with every display on the market. There are very few laptops that are stereo capable with using shutter glasses or polarized glasses or those weird things, whatever they give you in a cinema. Every computer in the world will work with red-blue stereo glasses. And if you want to try this out, you get the glasses at a comic shop. I thought these might be sort of obsolete technology. You know, didn't these die out in the 1950s or something? No. I went to a local comic shop, Impact Comics and Civic, said, can you get me 3D red-blue glass? And they're, sure, how many do you want? I had them under the counter. Okay, let's look at Bayer format. This is the internal sensor arrangement used by most digital cameras. You can see there's a 4x4 grid. It's got 1 red sensor, 1 blue sensor, and 2 green sensors. Apparently, the human eye is most sensitive to levels of green. So this is the raw format that comes out of your camera. And of course, there are only so many ways you can permute these 4 sensor elements, and different camera manufacturers have managed to do all of them. And Kodak have come up with yet another format where it's a 3x3 grid. Oh joy. But I'm not working with that one yet. I went. Now, decoding in Bayer format in real time is not really possible with current CPUs unless you're willing to do a really crappy job. Fortunately, it's a parallel processing problem, and that's tailor-made to run on a GPU. So I dug up this paper, Morgan Maguire Williams College. I'm sorry I haven't cited it quite correctly. It's a really good algorithm for de-Bayering or demosaicing into an RGB image. It requires OpenGL Class 2 GPU or Shader Model 3, and they're everywhere. They came out in 2005. My phone could run this code. Okay. Now I needed a library to put together this application, and ended up with GStreamer. This is what the Alpha Vision people were already using to record video sessions. If you haven't seen it before, it's a multimedia framework for Linux, and there are a couple of those around. It's based on glib and gobject, so technically it's part of GNOME, but it's not good. I like it. It is a really good example of Unix sort of modular design theory applied to this. So instead of a monolithic system, it's a bunch of little components. You can plug them in, you can extend them, and you can do nifty stuff on the command line. And I do like to demo this because it's very cool. These work. I'll talk about syntax prints out. Yep. In my checklist, I put on the notes, first couple of times I set up this talk demo, I've got a completely black screen. Eventually realised this because I forgot to take the landscape off. So let's have a look at this command line. So I'm using GSC launch. At the time I was doing development, GStreamer was officially version 0.1. Version 1.0 finally came out like last year. I haven't updated to it. So the other is, it's like a command line. In fact, it's basically a pipe using exclamation marks instead of verbal bars. So we start with the source. The source in GStreamer is something that generates video or audio. Although it's not a multimedia format, you can probably do any kind of real-time processing with GStreamer. It's that flexible. And the other end of the pipeline you need to sync, which just consumes data. So if you're traditional multi-processing notation producers and consumers. And here I'm using XD Image Sync, which is a very simple little plugin that just takes images that come in and feeds them into XD. So you don't need to write around custom viewer if you don't want to, you just plug it into an existing one. My source is an RCSP source. Way back in the 1990s, the Internet Engineering Task Force designed a UDP protocol called RTP, real-time protocol, specifically for doing video and audio. Now the problem is in the modern world of firewalls and NATs and so on, if you don't run over HTTP, you don't get used. So RTSP is basically RTP stuffed into a TCP stream that can be run over HTTP. RTP JPEG DPay is just taking the RTP stream. This is what I call a low-level component in GStreamer. It does a very simple function. There's one thing. RTP comes in, JPEG payload comes out. Then it's JPEG decoder thing. Again, it's converting. JPEG comes in, uncompressed RTP comes out. Then the queue, which just provides a buffering in the source. And here's a really interesting component, FFmpeg call space. How many people have actually programmed with FFmpeg out of curiosity as opposed to just in the utility? Good, yeah. I found it pretty hard when I was working with it, with everybody. Yeah. So the great thing about GStreamer is there's a whole bunch of wrappers around FFmpeg, so you get all the functionality of FFmpeg, which is amazing, and you don't have to learn the C API. You can just use these components. There's also a high-level component, it's a negotiator. So it doesn't have a specific input type or a specific output type. What it's doing is asking the components on either side, what do you want and what do you provide? So there's a video scaler, which is next in the pipeline. FFmpeg color space asks it, what's your preferred format? You want RGB, you want YUV, whatever. It goes back and asks Q, what are you providing? And the Q in this case is just going to say, well, I'm providing whatever JPEG is. JPEG. So FFmpeg color space then says, well, okay, my JPEG coming in, video source on RGB, I'll convert from one to the other. So again, GStreamer is a great way, using these high-level components, to just say, convert this into something that this will accept. Do we need to say anything else about GStreamer? No. So that's next time we've got to talk about. Another point is, I should have mentioned, it's zero copy internally. GStreamer just passes pointers to memory buffers. The slight downside of this is everything's running in the same address space, so if one of them crashes, it can sort of mangle everything else. But high performance, you need to do that with video. So my initial idea was, I'll just write a new component that fits in this GStreamer plugin. Debayering is really expensive on a CPU. My laptop, which is an Intel Core i5, it's not a wimpy, but it can't do real-time debayering. Now, for existing filmmaking procedures using the off-wall camera, that wasn't a problem. You just record the Bayer data. Later on, you run through a post-processing step and take however many hours it needs to convert to nice RGB. For this, had to do it in real time. So, camera sends RTSP over Ethernet. And my initial idea was that I'd write this debayer plugin. It would send the data over to the GPU, translate it into RGB, send it back. That way I'd have a nice universal plugin. I could contribute it to the GStreamer toolkit. It'd be usable by other applications. Problem is that once you've done this copy, it gets sent to the application, which in this case is doing a stereo preview, and it sends it straight back to the GPU, which is kind of inelegant. And you're actually talking about quite a lot of data here. 1920 by 1080 HD video is 2 megabytes in Bayer format, and it's 6 megabytes by the time you get to RGB. So that's a lot of data to throw around. So, new plan is I'm going to write a custom viewer app. It's going to be a GStreamer sync. It's going to take raw Bayer inputs. It's going to do conversion of RGB, display and stereo, all in one operation. But one of my development tools, once I've sort of worked out what I'm going to do, I decided to use Python as my programming language. If you already use Python, you know why, it's great. If not, It may seem an odd choice to use a high-level Python-like language for a high-performance video processing, but remember, the Python is not doing the heavy lifting. All the hard work of decoding the RTSP and converting to JPEGs or whatever, that's been done by GStreamer components. They're written in C and or assembler even in a fast. All the hard work of doing the debayering stuff from Bayer format to RGB is going to be done on the GPU. That's written in GL shading language. That's fast. So the Python is acting more as a traffic cop. It's just steering stuff around. I decided to use WX widgets for the GUI, and it was basically because I already knew how it worked, and this was being developed in a hurry. And OpenGL shading language, well, it's obligatory if you're going to do GPU programming. You can't write the stuff in C or C++ or whatever. You have to learn a shading language. So I ended up using an organic or spiral development process. I'm not big on test-driven development for this kind of project because so much of it depends on the end users. You can't really write end-user tests for your code. So I started with a very simple little program. Can I create a GStreamer pipeline from Python? Because after all, if that couldn't happen, I was going to have to rethink my development language. Then we moved on. Can I create a GStreamer component from WX Python? Then I started working in the application framework and just started with PNG files. And that was useful because I could then take it to my domain experts and say, imagine this was actually your video series, would it be useful to you? Fortunately, everything worked, and I was pleased to find that GStreamer, it meets the criteria that simple things are simple to do. I didn't have to write dozens or hundreds of lines of code just to get, say, a basic audio component up, and the hard things to do, they're possible without too much work. Now, part of this had to write a GStreamer component. Now, because they're G objects, this means you get to subclass existing templates. And the doco for GStreamer isn't great. It's sort of occupational disease of open source projects is everybody's too busy coding and to write any. But there are some nice example codes. Let's have a look at components. Because it's a G object, you end up writing a whole lot of boilerplate. And this is because, after all, G object is doing object-oriented programming in plain C. Now, my first reaction, since I had worked with GLs before, is why are we using C++? Something like that. Now, it's true that this kind of code is a bit tedious, but I realise now that it actually makes everything far more flexible. G objects can introspect, in the sense of all these properties, all the methods, that because they're defined explicitly through the C stuff, other programs can ask them what they are. Turns out that writing a Python wrapper for a GStreamer component is really easy, much easier than normally writing Python extensions to C. You just need a generic piece of Python code that's given the dynamic library, says, what objects do you use, what properties do you have, and what types they are. Oh, you've got an integer, it's called video source height. Oh, you've got a method that does this. So it's very easy to integrate these G objects into any language you like, Python, Ruby, JavaScript, for all I know. So now, every time I bundle myself up this is PDS, I realise it's an amplifier. G objects are actually more useful to people writing in other languages than any C++ object would be. Okay, getting onto the GL side. This is an area I think most Linux apps are going to start shifting to OpenGL for the rendering engine, simply because most of the frameworks have, and really OpenGL is about all you need these days. It does 2D graphics, does 3D graphics. Now, the problem is that a GL context is how you do everything in OpenGL. And it doesn't matter whether you're programming on a Mac or Windows or Linux, you end up with this equivalent object. And the old days it was easy. It was like a canvas or an X-drawable. It was just basically a window on a screen, a block of memory you wrote into it. These days, though, modern GPUs are best thought of as a loosely coupled asymmetric multiprocessor. It's a real CPU. It's got branches and exceptions and scheduling and all the rest of the stuff. It's got its own address space, and you're communicating with this thing through a kind of descriptor. And because we haven't really caught up on this sort of new model of what a GPU is, GL context, the objects through which we program, are not thread safe, and this causes all kinds of problems, which I'll now present. So my first application design, got two GStreamer pipelines, one per camera. The application was going to create its OpenGL context. After all, that's where I'm going to display the data, so it's going to pass those to the components and say, when you decode the BIOS stuff, put the RGB image here. And it would do that every time a frame came in. And in my test program, which had exactly one frame of data, a PNG image, it worked fine. Now the problem is, in a modern GUI, you've got an event loop. You don't actually write a sort of traditional main program. Instead, the event loop is the main program, and every so often it will call your code and say, you can execute now. And that's not unique to GNOME. It's how Windows works these days. It's how macOS works, which is okay for most purposes, but not if you're doing video or audio processing, because after all, if video data is coming in, you've got hard real-time schedules to meet. You can't wait for some event loop to decide, yes, you can execute now. So all the GStreamer pipelines are setting up their own little threads and running them by themselves. So on the left here, we have a bunch of frames come in. We've got a GStreamer pipeline executing repeatedly. And every so often it's going to try and copy data of an incoming frame to the GL context, which actually means send it onto the GPU. On the other side, we've got the event loop. And every so often that's going to say, well, I need to display something to the user for which I need the GL context. And you can see where this is going. It crashes badly. Go back. What I discovered, annoyingly, was that there's a call you use in OpenGL programming to acquire a GL context. And it's supposed to say either it's return true, yes, you can use this context, or false, no, I couldn't acquire that context. So I'd written my pipeline on the assumption that every so often I'd fail to acquire the context, I just have to wait and try again. This turned out not to work because instead it crashed. I'm not sure what's going on. One of the downsides of using Python and GStreamer and so on is there's so many different threading models going on, I can't figure out who's doing what. Occupational hazard. So instead of failing to occasionally copy a frame over, it was crashing. So version 2, I came up with this thing called the idle callback. If you're using GNOME, GTK, which WX Widgets is built on top of, you're allowed a one-shot callback next time the event loop executes. And inserting these callbacks is thread safe. So another thread can ask the event loop, when you've got a moment, execute this for me. So new design, the pipeline stuffs a frame, incoming frame into a buffer, tells the event loop, call this piece of code for me. If that sounds confusing, well, it is. I tried to draw a diagram of it. So the frame comes in, pipeline stuffs the frame into a data buffer. It's got this piece of copy code. It does not actually execute it. Instead, it passes the copy function and the pointer to the data buffer over to the event loop and says, execute this when you get a chance. Ideally, within the next 10, 15 milliseconds or whatever, the event loop says, okay, goes away and executes my copy code, which transfers data to the GL context. Now, one of the nice things about doing talks is that they make you revise your assumptions. My original notes to accompany this slide said, yeah, it looks a bit convoluted, but this is how modern GUIs work. And I thought, you know what, this is a really ugly hack. This is just a ridiculous way of working, and I think it's something that GUI frameworks have to work out, that we're not in a single thread, single processor era anymore. We've got these multi-core processors, zillions of cores all over the place. We've got to find a better way to do this. So while this works, in retrospect, I'm not so proud of it. Okay, buffer contention. You may have noticed in that diagram, it's possible for a new frame to arrive while the callback is executing. Now, I didn't put any locking on this, or scheduling, or queuing. So what's going to happen if these two events coincide? I mean, we're copying 2 megs of data. It can't be done in an uninterrupted operation. And the answer is the buffer contents get mixed up and you get a visual glitch. Now, any kernel programmers in the audience are probably blacklisting me for life now from ever working on anything important. But wait, this is a real-time 3D program. In real-time graphics, whether it's video games or simulations, or in this case, showing a video frame, frames are disposable. They get flashed on the screen for a 60th of a second and then they're gone. They're not being recorded. This is not the application that records the frames for the end user. This is just showing you, if one frame glitches, so what? You throw it away. So this is standard real-time practice. I would not recommend it though as a general practice. And the last thing I had to do was write a GPU shader, or rather, since I'd found that neat paper, copy the GPU shader code out of the paper and make it run. Okay, there's sort of 2 levels of GPUs on the market right now. There's the OpenGL 2 or Shader Model 3. They have vertex and fragment shaders. They're available for phones. They're available for Xbox 360 and PlayStation 3. They're available for Macs. They're available for desktops. Even a notebook with crappy Intel integrated GPU can handle that kind of stuff. The other generation, which just came out about a year ago, Shader Model 5, are very powerful, very advanced, and a little harder to get used. Now I want to show a shader here because some people think that sort of shaders are mystical magic things. Certainly I did when I started, but they actually turn out to be pretty easy. So vaguely written, of course it's not readable because it's on the wrong side of the screen. So looking at the syntax of this thing, GL shading language, it's basically C with vector and matrix types. You'll notice good old CPP, the C preprocessor, it's still there, it's still being used. And the code itself, it looks like C or C++, and that's deliberate. You have to learn a few new rules, but it's really quite simple. One of the best things about writing shaders is you're not writing a complete program. There's a whole bunch of scheduling and organising of data and so on, but you don't have to worry about that. The GPU driver does it for you. This is a very simple little program. It takes a pixel in, it puts a pixel out. So if you haven't tried GPU shaders, I recommend you do so. It's easier than you might think. Oh, wait. One last point, by adding GLSL to the mix, you'll now see that I've now got 3 programming languages in use. I'm writing in Python, I'm writing in C, and I'm writing in GLSL. Now that I think is just the way the future is, that this 21st century multilingual programming is the way to go. These specialised languages are all around us. You're just more productive if you can work in more than one language at the same time. I'd also point out there's a lot of frameworks. Even though this little application adds up to about 1,000 lines of code, I've got GNOME framework and WX widgets and GStreamer and an OpenGL driver. And it's traditional for programmers of my age, grey head, say, back in the 1980s you could program right on the machine and you knew how everything worked. Again, that's not going to happen. Those days are gone. Thank you. Okay, and speaking as a 3D programmer, the 1980s sucked. And the 1990s weren't much better. So actually, I'm glad to have all these modern frameworks. And yes, it makes life a bit more complex in some ways, but you can do so much more. So, finally, success. The program, which I haven't demonstrated, because for best effect you really need 2 cameras, and I've only got one of them. Nathan and Winnie built the rig. Sebastian put this stereo config stuff in AlphaVision. The little stereo cam check program I wrote proved to work with 2 cameras, so it was always fun. They used that to create a short 3D film. It was shot entirely in Canberra. It may have been the first 3D film in Canberra, I'd like to think so. I would like to say it was also been screened, but the filmmaker got seriously ill afterwards, and that hasn't happened yet. Okay, now pulling back, trying to make this more general. That was my project. Is anybody else interested in this stuff? And it turns out, yes. There's a community called Apertus. They're really big on free, in both the Grutty and Lieb sense, of software and hardware for filmmakers. So they run a software repository. AlphaVision is based there. Stereo CamCheck is based there. Used to be SVN. Now it's GitHub. They get contributors from Germany, which I think is where Sebastian is, from Brazil, from Australia, not just me. There's some people in Sydney working on this. They took their prototype sort of free camera and AlphaVision and Stereo CamCheck to the Pre-Arts Electronica 2012, which was in Geneva last year, and they were given a prize. And that's a fairly major electronic arts festival. So Blender has shown that you can make full 3D feature films from start to finish using only free software and using only free software. The Apertus people, their goal is to demonstrate that it should be possible to do the same with live action, all the way from filming. So they're trying to get people to develop software tools for converting, post-processing, video editing, all the complex stuff that filmmakers have to do, and currently they buy Macintoshes for. So on Stereo Cam Check, I've got this major to-do list of things. There's a colour shifting bug that when you move the windows, sometimes the colours in the image get swapped, so red becomes green and green becomes blue. GStreamer 1.0 has come out. Now, a big thing in GStreamer 1 is that they've introduced GPU components. So they're trying to set up a standard framework for copying data between pipelines and GPUs, and that would get around the problem I had. There's got to be a better way to compress biodata. Anyway, software projects are never finished. So it's traditional to sort of say, this is what I learnt, or this is what I want you to take away from this talk. So as far as programming goes, multilingual programming is the way to go. Learn C, learn Python, learn GLSL. GPUs are everywhere. It's worth learning about them, and GStreamer is really nice. And to wrap up, should thank Winnie and Nathan for bringing me in on this project. It's very informative. Elfoil.com, they're the people who make this camera. They're very Linux friendly, obviously. Not only are they using Linux in their camera, but they give you the source code, they give you the tools to update it, they give you kits. They're really good people to work with. And Apertus.org, which is where you find all these people who want to do free tools for filmmakers. And I have to say, Apertus, at the moment, I think there's more enthusiasm than technical ability. And that sounds harsh, but I think it's true. And if you're a programmer and you're interested in working on this kind of stuff, on interesting projects, they could really use your help. And that's it.
Thanks, Hugh. We'll take some questions. So just put your hands up so I can... Oh, good.
Thanks for that. Would you mind repeating what a shader actually does?
Okay, on the GPU, there's two kinds of shaders, at least for the simple one. Vertex shaders handle geometry. So you send in triangles or quadrangles or whatever your shape is. Think of them as vector graphics, kind of stuff that comes out of Inkscape. And you can translate them or distort them or transform them. Fragment shaders or pixel shaders take individual pixels. They come in and you can do whatever you like to that pixel. You can't actually move it on the screen, but you can change the colour space. You can look up a table and translate it. You can do colour blending. You can convert colour images to grayscale. All those super duper effects you see just these days in the GIMP or Photoshop, they're all done with shaders. So anything you can do, pixel comes in, another pixel comes out, that's it.
Sorry, hog the mic. I had one more question. Would you mind showing us, you mentioned it didn't take very much Python to hook up to that GObject stuff. Could you have the piece that hooks up to that you could just quickly show us?
This is a very simple little Python library I wrote. It's just doing boilerplate stuff. You can see that compiling a shader, just taking a piece of code from a file. It's half a dozen lines, and most of those lines are actually filling out where the text comes from. All the real work is done here. Compile a shader, did it work? You also have to what's called link a shader. Did it work? Half a dozen lines of code. More gstvideo.py. This is the stuff that actually does useful things with it. So here's code that creates the fragment shader from a file. You can see it's just a couple of lines because I've already written it. When I want to use the shader, I need one line of code, Jill. I'm just inserting this little filter. As I said, they're not complete programs. They're little kernels, is I think the word, if you've done signal processing. Pixel comes in, pixel comes out. It's more like a function. Yeah.
This is an unrelated question. When you're doing the 3D display, are you displaying alternate frames or alternate lines, or how are you interleaving the two sets of video?
RGB glasses, so the red pixels are one eye,
I understand
green
how
blue
it
the
works
other.
for the eyes. I'm wondering how you're doing it from the camera to the display. Are you displaying 30 frames from one and 30 frames from the other interleaved, or are you trying to merge the frames in some
They're
manner?
merged. That's what you do with red, green, blue. Is it's merged in colour space. So I convert the red, green, blue from the left eye into a grey value, and then I copy that.
So you're doing 2 sets of debarring and then interleaving the frames you're getting.
Hang on a sec. This is the actual code here. So for a given eye, I calculate the grey value. It's more like polarised rather than shutter glass. So shutter glass stereo goes alternate left then right. Polarised displays at the same time and separates by polarisation. Red, green, blue, you overlay 2 frames. One of them is only written to the red pixels of the frame buffer. The other image is written to the green and blue pixels of the frame buffer. So when you view the information, the red filters out one eye and the green and blue filters out the other.
Thank you.
It sounds more complex than it really is. Red, green, blue stereo is very easy to write. Yeah,
Then I understand it was how it fell back into your pipeline.
yeah.
All right, well, I think we've just about run out of time, and with all our guest speakers, we have a presentation from LCA 2013. Keep your project warm, and thank Hugh for his excellent presentation.